So hello everyone. My group members and I did our project on conductive ferrofluids to make reconfigurable liquid circuits for computing applications. My name is Apurva Chanda.
I'm Megan Stalick.
I'm Eileen Rashid Faroki.
I'm Ethan Wong.
And I'm Josh Wrong.
All right, so you may be asking, why are liquid circuits better than solid circuits? And the answer to this is solid circuits are embedded in silicon chips, and this means that whenever this technology comes out, you're pretty much limited by it. You can't change it in any way. So the benefit of a liquid circuit is that you can reconfigure it to optimize it to the best technology that we have to date. And pretty much all you have to do is download a schematic and then apply it to your circuit so that it can create different pathways and different combinations that would be favorable.
So we first asked the question, what can we use to make our liquid circuits? This question was actually fairly easy to answer, considering that ferrofluid is the only liquid that is easily manipulable, like easily controllable. And then this is because it is a combination of conductive magnetic nanoparticles with the properties of a liquid. So when you apply a magnet, it easily follows the magnet, but when there's no magnet applied, it acts like any other liquid. And fun fact, it was first used by NASA to move fuel in space.
So our main research question was, how do we make these ferrofluids conductive enough so we can use them in computers? And we hypothesized that a salt solution would be the best for this because it would produce enough ions for our ferrofluid to be conductive enough. And so the main impact and significance of our research was that it would create long-lasting technology. We wouldn't have to keep rebuying our computers, TVs, and phones, and instead we could just update as long as new technology was invented. And actually, ferrofluids have been used in computers before. They're used in hard drives to protect rotating elements in computers from being contaminated by dust and dirt. So we decided to take this a step further and use ferrofluids in other parts of a computer.
So here we have a diagram of the model that we made to test this liquid circuit. And right there would be the ferrofluid, and it's connecting this one circuit right now, turning on the red LED. And it can be manipulated and moved to different circuits and turn on the different lights, representing the different bits of the computer. And we do this with a magnet on the bottom, and we can use it to drag the ferrofluid to wherever we want on the slide, completing the different circuits.
All right, so we designed our experiment in the following way. So we, as Josh said, we constructed our circuit in the way with 3 LEDs connected to a battery with switches in the that sort of interrupt that circuit, and then these switches can only be turned on when the ferrofluid makes contact with both copper contacts, and then whenever the ferrofluid completes that circuit, we should see individual LEDs turn on. So in order to understand how the ferrofluid works, we kind of have to understand how we synthesized it. So we used iron chloride solutions and a base called ammonium hydroxide, and when we mixed it, we created iron oxide nanoparticles and a byproduct called ammonium chloride. So in this video, we can see how we synthesize this. Whoops. Okay, so as you can see, in the brown liquid is the iron chloride, and then what we're pouring in is our base, ammonium hydroxide. And as we're pouring it in and swirling it around, you can see that the color of the solution kind of changes, and this indicates that we're creating a new compound, which is our iron oxide nanocrystals. And as you can see, it's kind of black, like the images we saw earlier of the constructed ferrofluid.
There was one specific reason why we decided to go with the ferrofluid. This is because this fluid is easily manipulated. When it's surrounded by a magnetic field, it can be controlled and it does what we want it to do, but without it, it acts like any normal liquid. So we decided that this would be an easy thing to control and a best choice for us.
So as you can see in the video, as the ferrofluid is put on the plate, and there is a magnet under the plastic that is moving the ferrofluid, and as it moves, the LED lights are turning on. However, the ferrofluid was not as electrically conductive as we had expected. That's why the lights are fairly dim, but the ferrofluid is very easily movable to control, and it's fairly reconfigurable. So because the ferrofluid wasn't as electrically conductive as we had expected, we added salt to it, which caused the LED lights to be much brighter. However, it was harder to control the ferrofluid, and since there was salt in the ferrofluid, it stuck to the plate a little.
Looking at the side-by-side view, you can clearly see the difference between the brightness in the LED bulbs. Specifically, if you look at the green bulbs, the top solution is the one without salt in it. It is less conductive, but is easily workable. As you can see, only one LED is on in that picture, as opposed to the second picture with salt. The bulbs are brighter, but all three bulbs are on, as we were unable to move the ferrofluid as easily as the one without salt. So this relates to a computer chip because it's kind of a proof of concept that we can manipulate which LEDs or like which bits we turn on, and when it's off, it represents a 0. When it's on, it represents a 1, like your binary in your computer. This is kind of like a proof of concept because if we can switch between these 3 LEDs, we can, in theory, switch between as many ons and offs as we would need to.
All right, so in conclusion, this demonstrated that we can use a conductive magnetic liquid. In this case, we used a ferrofluid, and we used it to construct a reconfigurable liquid circuit. So if this were a solid chip, it'd be impossible to reconfigure the connections without a mechanical switch. So this is a new area of research that can produce some promising results in the future. We just need to sort of fine-tune it and sort of get a bit better at controlling our magnetic fields.
So some possible future applications is that we could have a liquid computer chip as long as we are able to manipulate the ferrofluid precisely and control the magnetic fields. Additionally, today our software is updated multiple times a year, but our hardware is not as of now. And if we use this system, our hardware can be updated as frequently as our software.
Any questions? Yes.
The processing chip doesn't just have a switch to do on-off, it has transistors, diodes, and all those things. How do you think you can make those kinds of components using ferrofluids?
It's still a pretty new. Oh, okay. So the question was, right now, computer chips use transistors and diodes, not just turning on a switch. So this is a pretty new area of research, and we think that as we go deeper into this area of research, we can figure out new ways to to replace what we're using right now as physical chips. But as of right now, we're not really sure how that would work.
One thing that's very striking about your video is how much more viscous the ferrofluid looks after you've added the salt. At this point, would you speculate if you had unlimited time, would it be different concentrations of the salt or a different compound to make it conductive that you would try next?
So the question was about the concentration of the salt, how it made the solution much more viscous. And yes, if we had more time, we would play with other ionic solutions to not make it as viscous, but still more conductive. We were looking at like citric acid, but unfortunately we ran out of time. We're unable to try those.
To add on to that, we did use lower concentrations of our salt water, our ionic solution, but when we mixed it with more water, it sort of made our iron nanocrystals fall out of the solution, so it wasn't suspended in the solution anymore, and it was all the nanoparticles were sedimented at the bottom with all the liquid at the top. So yeah, in the future, we would like to explore different ionic solutions. Yeah.
So, a lot of your work in trying to help control the ferrofluid moving along the surface better was focused on editing the flow mechanics of the fluid itself. Did you think at all about maybe a way that you could manipulate the surface so that it moves better between the different switch states?
Yeah, so we were, at first we were planning on using a hydrophobic and hydrophilic surface in order to create pathways for our ferrofluid to follow. But the problem with this is that we were trying to use we were going to coat it with DCT and MUO, which are respectively hydrophobic and hydrophilic surfaces, but those only bind to metal, and we didn't have the materials necessary to do that. But we also changed our glass slide at first to an acrylic slide because our original ferrofluid it stayed on the surface instead of spreading out and staying where instead of staying where it was when we were moving the magnet. Yeah.
You mentioned that the nanoparticles were crashing out when you had low concentration of salt.
Yeah.
Why was it crashing out?
Well, we first mixed it with salt water, and we're not exactly sure why it crashed out. Except we have some theories. Maybe the coating on the iron nanocrystals, which was a polar compound called TMAH. Maybe that wasn't strong enough to withstand, I don't know, some of the different forces within the ionic solution.
Students, any questions from you guys?
Thank you.
Some good questions for the next one.
Thank you.
Thank you.
Thank you.